Section 8.4 is other convergence tests or further convergence tests. So we'll first introduce an alternating series, and then its convergence test that's related to it. An alternating series, we've seen these as sequences so far, but now this is a summation of these sequence terms. So it is, in fact, a series. And the plus or minus sign is going to alternate. That's why it's called an alternating series. We're positive, then we add a negative, then we add a positive, then we add a negative number, add positive, add negative, and so on. So that's how our series alternates, and that's how it gets its name. So the question about a series like this, well, we might recognize this without that -1 factor. So without the plus or minus sign changing, alternating as it is, we might recognize that this is the harmonic series if it was just all plus signs instead of minuses intermixed in there. So we know that the harmonic series diverges as, well, as a series. Now the question would be, will this series, which is, I guess we could call it the alternating harmonic series, will this series converge? Because if you think about it, we're going to take 1 minus 1/2, so we'll shrink a little bit, then we'll add 1/3 to grow a little bit, then we'll shrink a little bit, grow, shrink, so on, in terms of our partial sums. So this is a good question. It might, when we see this summation, we're not quite sure if this thing should converge or diverge just by inspecting it, because we know that the harmonic series itself diverges. So it's a very good question here. This kind of leans towards maybe being in favor of convergent. So one way to inspect that is to look at the partial sums. S1, the sum of the first one term is just 1. S2, the sum of the first two terms, 1 minus 1/2 is 1/2. Similarly, S3, the sum of the first three terms, that comes out to 5/6. So we might ask ourselves, could this thing converge? And we'll actually get to the proper answer of that in just a little bit. So we're leaving that as an open question for now. Now, next up, we've got another one, -1 to the n minus 1, this infinite series. So when n equals 1, we have 1 minus 1 is 0, and -1 to the 0th power is 1. Our second term is -1 to the +1, so that's -1. -1 squared is +1. -1 cubed is -1, and so on. We see that this one is also an alternating series, and the terms are just all ones in this case. When we look at its partial sums, we see S1 is 1, S2 is 0, S3 is 1, S4 is 0. We can quickly see that any odd terms are going to be +1, any even partial sums will be 0. And if we recall the definition of convergence for a series, we would note that the partial sums need to converge as a sequence to some value for a series to be convergent. Well, this sequence of partial sums, 1, 0, 1, 0, 1, 0, is not a convergent sequence. It oscillates between 1 and 0. It never gets arbitrarily close to one or the other without leaving the other one behind. So in other words, we can go infinitely far out on the tail to the right and still pick up a place where we jump from 1 to 0 or 0 to 1. So we know that this is a divergent series just by inspection. Okay, so there's a main characteristic that we want to keep in mind between this series and this series. So the second one we have seen is divergent. The first one is still an open question. Now, the reason that the first one still has a chance of converging is because the terms, as we go out further and further in the series, get smaller and smaller. They're getting closer and closer to 0. So that's a helpful thing. Whereas in this second series, these the terms, it doesn't terms, I mean, without plus or minus signs in front of them, the numbers that are actually being put in here, these numbers don't change. They're all ones the whole way through. So this thing is, of course, going to have some kind of oscillating behavior. So let's see what we've got for tools to assess convergence. It's the alternating series test, and this is what allows us to test for convergence for any series that alternates. Okay, it's actually a pretty straightforward test. It's a little easier than a couple of the ones we've already seen. What we'll do is we'll split these b sub n terms, noting that they're positive, they're greater than or equal to 0, right? That's the portion of the series that's not alternating, just the b sub n. Okay, and we'll inspect that as its own sequence. So let's not be confused. We're still assessing the convergence of a series, but in order to do so, we look at the sequence and we look at the terms of the series, b sub n, as a sequence, and we ensure that each subsequent term, b sub n plus 1, is less than or equal to b sub n. In other words, that this sequence of terms is decreasing, so that every subsequent b sub n is smaller than one before it, or at least equal to it, or at most equal to it. Okay, and again, that's just taking these as positives. We ignore the plus or minus signs. Now, the second part of this is that the limit as n goes to infinity of these b sub n terms as a sequence, this is written as a sequence right here, converges to 0 as n goes to infinity. So, so if our terms are decreasing and they have a limit of 0, then we can conclude that the alternating series is convergent. Now, there's a nice proof of this in the book. We'll forego that here just for the sake of using this result and getting to understand it that way first. So let's see a couple examples. Determine whether or not the given series converges. This is our alternating harmonic series that we saw before. Now we're going to use our alternating series test on it to determine whether or not it converges. We note that b sub n, that's getting rid of the plus or minus alternation in it. So it's anything but the -1 to a power term. So b sub n is 1 over n. And now we want to check two things. Is this a decreasing sequence? So in other words, is b sub n plus 1 less than or equal to b sub n for all n greater than or equal to 1? Well, write down what that means. We're asking, is 1 over n plus 1 less than or equal to 1 over n, thanks to the definition of b sub n? And, well, one quick flip here, and remember to change the inequality sign to less than or equal to or greater than or equal to. Or what we've done is we've done n plus 1 times 1, cross multiplied n times 1. This ended up over here, and this ended up over here on opposite sides of that less than or equal than sign. But at any rate, we arrive at an equivalent statement to the first one, which is this, which we know to be true for all values n greater than 1. N is less than or equal to n plus 1 for any n value that is greater than or equal to 1. So this is always true for the values of n we're interested in, and for any value of n for that matter. But we just need to worry about those values. So the second thing, we move on and we'll say, okay, well, this is a decreasing sequence. So let's see if the limit of these terms is 0 as n goes to infinity. And in fact, the limit as n goes to infinity of 1 over n is 0. It's a pretty easy limit to write down. In fact, there's not really much work to do. That's it right there. So both things check out. We have a decreasing sequence of series terms, and the limit of these series terms as a sequence is 0. So it passes both conditions of the alternating series test. So we say that by that test, S converges, or series converges. Okay, now if one of these two conditions were to fail, let's look again at this situation. If this situation were to fail, the second condition, part B of the alternating series test, if it were to fail, then we would be failing the divergence test. So that's a really important thing to keep in mind. So if your series doesn't pass part A, well, maybe you need to dig a little deeper to determine whether or not the alternating series converges or diverges. You know you can't prove that it's convergent with the alternating series test. So what you'd probably want to check next is the second condition, because if it fails the second condition, that's the criteria for the divergence test. When it fails the second condition, the divergence test tells us automatically that this is a divergent series. So keep that in mind. You check both conditions. The first one fails, maybe move to the second one, because that'll give you handy proof that the series is divergent through the divergence test. And that's typically how all the problems will go for these alternating series test problems. Now, another one, S is the series, it's alternating, and then it's 1 over n times natural log of n. So this is a good question. This thing should move a little bit faster than the previous one, and it should converge. But let's recognize that b sub n is equal to 1 over n times natural log of n. We're going to do this thing formally. We'll apply our alternating series test. We want to check that this is a decreasing sequence of series terms. So as b sub n plus 1 less than or equal to b sub n for all n greater than 1. And we write down what that means on each side of that inequality. We have a statement that looks like this. Now we'll multiply, um, cross multiply again, and we end up with n natural log of n is less than or equal to n plus 1 natural log of n plus 1. So, again, we multiply both sides by this denominator, and it ends up over here. We multiply both sides by this denominator, and it ends up over here. So we're on these correct sides of the inequality that we have down here. And inspecting this, we realize that the natural log is an increasing function. Remember, its graph looks something like this. As we move outward, we move upward, so it is increasing. So if we put a larger value of n in over here, it's going to be larger than the natural log of it's going to be larger than the natural log of n. It's true for all n greater than 1, and we also know that this is greater than n as well. So it's pretty easy to say that this is this holds. This is an decreasing sequence thanks to this holding. Okay, so b sub n is decreasing. Our first check is passed. Now we have to pass our second one. We take the limit as n goes to infinity of that series term, n natural log of n, 1 over n natural log of n. And this one also goes to 0. That's because we recognize up here natural log is increasing. As n goes to infinity, natural log of n goes to infinity. So that's an infinity times an infinity down here in the denominator, though we would never write that. That's how we're thinking about it. This is growing arbitrarily large as n goes to infinity, so it's driving the whole expression to go to 0. So we've got both conditions. The sequence of series terms is decreasing. The sequence of series terms has a limit 0 as n goes to infinity, and we can thus conclude through the alternating series test that S converges, or series converges. So we've seen another one converge. So for one more example, we'll look at an alternating series of this form. We've got, of course, the alternating term, and then arctangent of n will be our positive term, our b sub n's. So one of the first things we can really use here is just the divergence test and say that this thing is, we can note that this limit does not exist. Now, that's a pretty bold claim. Maybe we do a little bit more work before we get there, but this answer is being formulated in a way that one might write it as a mathematical proof or mathematical demonstration that this is the case. And of course, we want to prove that these series are divergent or convergent. We don't want to claim that. We want to be able to show it mathematically as we do below. So the first thing we would probably check is this. We'd say, what's the limit as n goes to infinity of arctangent of n? What's equal to pi over 2? In fact, if we think about what the arctangent of x looks like, or n, for a continuous curve, I'll do it, that's for x, it's asymptotic horizontally, right? This is what arctangent of x looks like, more or less, and the origin somewhere about here. So this is actually not, so if we start at n equals 1, as we have right here, then we're starting somewhere about here. And this is not a decreasing sequence. So the alternating series test will not show that this thing converges if it happens to converge. So we'll leave it alone. We see that it's not increasing because as we go this way, we're moving upward. All right, so it's a good chance that this thing diverges, but we can't show it through the first step of the alternating series test. We have to look at the second step, and that's why we're immediately looking at the limit in this case. So the limit of arctangent as n goes to infinity, well, that horizontal asymptote that was here, just to rewrite it, is actually pi over 2 above, and it's negative pi over 2 below if we're going to the left, but we're only going to the right because n is increasing. So it's not 0. So and we've got pi over 2 written here, essentially thinking of that graph or just knowing how arctangent behaves. So it's not 0, it's pi over 2, and now that means that this series term will fail the divergence test, right? So this is not 0, so we're failing the divergence test. And really, this limit being what it is tells us that as n increases and we alternate, we're bouncing back and forth between negative pi over 2 and positive pi over 2, or nearly between negative pi over 2 and positive pi over 2, right? Because we don't quite get there in the limit. We're just approaching it as n goes to infinity. So this thing does not converge. The divergence test tells us that because its term, its limit doesn't even exist, right? It's alternating, its limit doesn't exist, so it's going to fail the divergence test, who says that a series whose limit doesn't exist or whose limit is not zero does not converge. So we're able to use the divergence test on this. So that's all been written in sort of a backwards order. When you got done doing an analysis like the one we just did, you might frame it in such a light. Maybe you put things in, maybe starting with this order, as long as it makes sense and is coherent. In other words, a key word here is saying that this is the case since, and then what follows is the justification. That's just as well as giving the justification and then making the conclusion. So when an alternating series does not converge, you'll most likely show that it's divergent with the divergence test. So let's look at one more thing before we end this first of the two videos for 8.4, and that's estimating sums. So if we're given an alternating series with positive terms b sub n, and then alternating -1 to an n power term, and we have that it's increasing, and its limit, so its sequence, its series terms increase or decrease as a sequence, and its series terms have a sequence limit of 0. Okay, so in other words, it's a convergent series. Then we can approximate its error in an estimate. Okay, so we can estimate the sum with S sub n, and then what we'll know is that the remainder, or the error, is less than or equal to b sub n plus 1. So in other words, the error, if we use the nth partial sum, is bounded by, we're going to be no more incorrect than b sub n plus 1. It's a really handy, quick estimate with error bounds to have on hand for these things. And I'll show you why that's the case when we do the example below. It's pretty easy to see with an example first, and then you could go back and analytically reason through it as well. So note that this is the error. The remainder of the series is the error. It's what we didn't add up when we approximated the series with S sub n. So the difference between the actual sum and then the approximation S sub n that we use. Okay, so they tell us to approximate the sum of the series to 4 decimal places, and we have -1 to the n plus 1 over n to the 6th. So I know ahead of time that this is going to work for the first 4 terms, and we can clip it off there. We have 0.985502. We can round that to 0.9855. Now, if I want to check that error, or if I wanted to check before I wrote this down, should I go to plus 1 over 5 to the 6th as a next term in here? The reason I knew to stop was because I want to ensure my accuracy. I write down 1 over 4 to the 6th, and I know that that's not quite going to have 4 zeros in its decimal place, though it's close, but 1 over 5 to the 6th probably will. In fact, as soon as we see this, we realize, yeah, that's going to have at least 4 zeros in its decimal place. And an approximation of what that value is 0.00006. And what I'm looking for is these 4 zeros in this decimal place, because I want to be accurate within 4 decimal places. So that's my check. The last thing I might want to do is see if I add this 6 to this place right here, will it change what this number is? Well, maybe in rounding it would to some degree. So maybe we would carry it out one step further, and then it would round up to 0.9856. But I think we'll have some error tolerance in any of especially the written assignments that we do, but and perhaps even in WebAssign. So probably the best in this case would be to take this all the way down, add the 1 over 5 to the 6th term, because it does affect how that rounds, and then we'd have it correct to 4 decimal places. So I cut off a little too soon here, but it's good to notice that based on the situation. Now, why does this error bound work? That's what I'm more interested in. Why is S sub 4 minus S at worst an approximation this large? Well, think about how things are being added up. If we cut this series off, this infinite series, this infinite sum off right here, then the next thing we would have added is a positive 1 over 5 to the 6th. After that, we would subtract 1 over 6 to the 6th, and that would be a little bit less than 1 over 5 to the 6th, so it would make this less than that. And then we'd add something even smaller than that. So the worst our error could be is exactly the next term. It's exactly this 1/5 to the 6. That's as bad as this could be in terms of error, because any more terms are going to bring it down and then back up and hone in more and more on our actual series value. So that's why this thing works. And note that in this case, this should probably be 0.9856 to be a little bit more accurate. Of course, in written assignments, assessments, and things like that, that won't be as strict, but WebAssign might be a little bit more picky. So that's it for the first video for 8.4. In the second video, we'll see one of the most important convergence tests of all. That's the ratio test. And then we'll move on to a little bit more of an esoteric test called the root test. And that should close us up for 8.4.